Welcome to Ask and Learn.
For this problem on the topic of equilibrium of rigid bodies, we are told that a uniform 10 kg rod, as shown in the diagram, is being supported by a ball and socket joint at position A and by a cord CG attached to the midpoint of the rod, and this is connected to the wall at point C. Now the wall is vertical and frictionless, and we are asked to calculate the tension in the cord as well as the reactions at A and B. So if we look at a free body diagram of our system, we can see that we have broken up our reaction forces into its components along the various axes. So firstly, we know the weight of the rod, W, is equal to mg, and this is its mass m, which is 10 kg times the acceleration due to gravity, 9.81 meters per square second. And so the magnitude of the weight is 98.1 newtons, and this is obviously vertically downwards at point G. Now the vector GC we can write as minus 300 times the unit vector I plus 200 J minus 225 K. So I, J, and K are the unit vectors along the X, Y, and Z axes respectively, as we've shown in our diagram. And the length of GC is 425 millimeters. Now the tension, the vector tension in the cord T is equal to the magnitude of the tension T times the vector GC divided by the length of GC. And so this is T over 425 times the vector GC from above, which is minus 300I plus 200J minus 225K. Now we need to express more vectors. So firstly, the position vector of B relative to A, RBA, is minus 600I plus 400J plus 150K, and that's in millimeters. The position vector RG slash A is minus 300I plus 200J plus 75K. Again, this is in millimeters. Now, since the system is in equilibrium, the rod is not moving, the sum of the moments about A must equal to 0. So R of B relative to A cross with the reaction force B plus R GA cross with T plus R GA cross with the weight. The weight here is minus W, which is the magnitude of the weight acting in the negative Y direction, so that's minus J, and this must all equal to 0. Now we can use the method of cofactors to calculate the sum of these cross products. So that's I, J, and k, plus the second cross product. Again, we need I, j, and k, plus the final cofactor method, I, j, k. So for the first cross product, we have minus 600, I, 400, j, 150k, and b is purely along the x-axis, so only has a component in the I direction. That's b, 0, 0. The second cross product is minus 300i, 200j, 75k, crossed with minus 300, 200, and 225k, minus 225k. And this is multiplied by the scalar, the tension, over 200 over 425, plus the final vector, which is RGA minus 300, 200, and 75 crossed with the weight, which is 0 minus 98.1. We calculated this earlier, and 0. So let's solve these cross products and write down each component one at a time. So the I components gives us minus 105.88 minus 35.29 times t plus 7,357.5 is equal to 0. So from here, we can immediately find the tension. So the tension T, if you rearrange this equation, which is the first required solution, is 52.1 newtons. So we have the magnitude of the tension as required. Now we can immediately go to part B of the problem. And going back to the sum of cross products, we can take now the J components. And the J components give us 150B minus 300 times 75 plus 300 times 225 into the tension 52.12. Above, we've taken the significant figures into consideration, over 425, and this must equal to 0. So again, we have one equation with one unknown, which implies that the reaction force B, which acts only in one direction, is 73.58 newtons. And so the reaction vector B is equal to 73.6, keeping the significant figures in mind. That's newtons along the I direction. And so we found our first reaction force, which is B. Now we're left with one more, which is A. Now we can use Newton's second law, and this says that the sum of the forces must equal to 0 since the system is in equilibrium and there's no acceleration, which means that the reaction force A plus the reaction force B plus the tension in the cord minus the weight must equal to 0. So taking I components of this equation, the coefficients of I, we get AX, the X component of reaction force A, plus 73.58 minus 52.15, and using some geometry, that's multiplied by 300 over 425 is equal to 0. Remember, the weight has no vertical components. And so from here, we get the x component of the reaction force A to be minus 36.8 newtons. Now taking coefficients of J, we have AY plus 52.15. Remember, B has no vertical components, into 200 over 425, the vertical components of the tension, minus the weight, 98.1, must equal to 0. And so again, we have one unknown, and we can find this unknown, which is the y component of the reaction force A, and AY is 73.6 newtons. Now finally, we need to find the z component of the reaction force AZ. So we take the k coefficients of that equation. So we get AZ minus the z component of the tension, 52.15, into 225 over 425 must equal to 0, which implies that we can find the final component of the final reaction force A, AZ, to be 27.6 newtons. So in essence, we have found the reaction force B, and now we have found the reaction force A.